Okay, so moving on, carrying on from part 1 to part 2 with the refresher video series. There's a couple of things that I wanted to touch on, which was modal interval. I skipped that one. What I mean by modal interval, here on our axis again, let's say we separate these out by 10%, 20, 30, 40, 50, 60, and this is from 0 to 10, 10 to 20, da da da. And we were going through some examples here where we were using students, the number of students in a test, in an exam, that had received between 10 and 20%, between 20 and 30% on the exam, or 3 between 30 and 40, 2 and including 40, or 6. So a modal interval is the one that has the most, and in this case it would be 7. If 8 had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 students that I've counted, and I'm using ones just like basically like old school where we used to do 1, 2, 3, 4, 5. I'm just counting. So a modal interval in this case would be over here, would be this one. This has the largest count. The mode, M-O-D-E, of any calculation is the one with the largest count. So in this case, the mode is, we counted I think 10 here. So the mode is 10, the second mode is 7, the third is 6. Do you see? Because we're counting 6 or 3 observations, etc. in these modal intervals. Modal interval. That's something I skipped in part 1. And the other thing that I wanted to touch on as well was median and central tendency. Here, let's clear the canvas. Again, I'd like to use, so how about this? Again, we're going to show a bell curve like this. This is 0, this is 100% of observations of students, and the central tendency is an average. It's this average over here. It's this here. This is the central tendency. And what this means for a set of data is that no matter where our points lie, there is one value, an average, which we refer to as a central tendency, or we start using as an example of the data. That's a central tendency. The median, just because we didn't specify it earlier, in this case, you see I have 1, 3, 6, over here, I think this was a count of 10. So if I did my averaging, I would do a sum of 27, and you actually see here 5.4, the below you see 5.4 is the average. The median, you have to do your values in ascending order, which I happen to have. So for instance, let's say I did 1, 2, 3 here as well. I need to place these values in ascending order, and what I mean by that is right click, sort, smallest to largest, which obviously messes up the rest of the values, but just to give you an idea of what we're doing, we have 1, 2, 3, 4, 5, 6. So we're going to take the middle 2 values, 3 plus 6, which is 9, divide that by 2, and we get a median of 4.5. Let me take this back. If we had 5 values, let me get rid of this, delete, I would just take the 6. Basically, median is the middle number. And I want to show you median, the calculation that Excel does. You grab the values, and it will make the calculation for you, and it will just take that middle number. Earlier, we also had another 3, and we said it was 4.5 was the median. So there you see, this gives us the 4.5. We did some examples of quantiles and then quartiles, quintiles, which was, if you recall, 25, 20%, etc. And what I wanted to show you is how to make a calculation of a quantile or a quartile. So let's say we have these values of test results for our students. Go back again. 1, 3, 6, 7, and 10. So 1, 3, 6, 7, 10. And you see we have these results. These are hard results. So if I were to say quintile, if you remember those were at 20%, I would say in the first 3 quintiles, which would be 20, 40, 60, 60 divided by 100, and I have n plus 1 observations, or I have 6 here, I have a calculation of 6 times 0.60 equals 3.6. So basically what that means is we will go to location 1, location 2, location 3, or our 6 here, and say 6, and then this 0.6, which would be 7 minus 6, or 1, times 0.6 equals 0.6. So we would say 60% of our observations, 60% of our observations here, let's change this color. Make it a little bit, make it bigger. 60% of our observations, 60% of our observations lie below 6.6%. And I would venture to say to and including 6.6%. And we did the 6 because when we did the calc, we had a location of 3.6. We counted the location, which gave us the 6 number, and then we took 7 minus 6 times the 0.60 so that we could find another location, which gave us the 0.6. So at location 3.6, by the way, if this was an 8, we would have had 8 minus 6, or equals 2, and we would have had 1.2, or rather the 6 plus 1.2 equals 7.2, and I could have made the statement that 60% of the observations will lie below 7.2, the value 7.2. And so that you can see the math, the actual equation behind how we can count. And you can do this with quartiles, with quantiles. You first have to find a location, and that would be your number of observations plus 1, and you multiply that by whatever you're searching for. In this case, let's say we're looking for 3 quartiles, or 75% over 100, so that you can get some kind of a location. Once the location is found, go and find that observable value, and if there's any remainders, calculate out the remainder. Next, I wanted to touch on the calculation of dispersion and what that term actually means. And the way I have that documented is that dispersion is the spread around the average. So we keep drawing our distribution over and over again as a bell curve. This is the y-axis, this is our x-axis, and this is our distribution, let's say student test results. This is 0, let's say this is 7 for 70, and this is 1 for 100. So we'll make this a 0.7. This is the central tendency, or the average. This dispersion, all of this over here, is an explanation of what is happening around the mean. That's dispersion. Next is a range. Going back again, the range will give us a minimum and a maximum value. So we have a min and a max. That's our range. We could also have a range for an interval. We were speaking about different groups. These are also ranges. But generally speaking, with dispersion, range is a minimum and a maximum value. And I want to touch on what is MAD, M-A-D, the mean absolute deviation. So we're using an absolute value, and just real quick, again, let's go to the whiteboard. An absolute value is something like this, would equals a 1. That's an absolute value. So -3. You'll get these straight brackets will equal a 3. That's an absolute value. And let's go back to our dispersion calculations. Now you have a better idea of what is dispersion, the way the data is set up around the mean. And if you recall from our example in part 1 of this refresher video, we were doing some calculations on different means. So here's absolute, basically taking the absolute of B6, and if you remember, this was the observation minus the mean, and we could be using any mean. We are ending up using what's in A10, which is our symmetric mean, our typical average mean, our average, say. So we're not using geometric or a different type of average, like the harmonic. And I'm taking the absolute value and summing it up. I am summing it up and then dividing by the number of observations. In this case, if you recall, we had 5 days worth of stock returns. By the way, these are prices. If you really want to do this, use returns or the delta, which we're going to touch on subsequently when we tie everything together, because this eventually will get into our portfolio presentation. This eventually is leading to a research report on portfolio diversification. So all of these terms, view it as if you will be presented with a research report on a portfolio. That's who I'm imagining I'm speaking with, but also I was visualizing you're speaking with educators, researchers. I mean, imagine if you're speaking with people just covering COVID. How would you explain some of the statistics behind how we're measuring the spread of the disease? So it doesn't have to be stocks. I like stocks because I'm very interested in the market and diversifying and investing. I'm very interested in good companies and investing in good companies. So this is just another way of researching them, of looking at these companies. Here's MAD, the mean absolute deviation, and the result, as you saw, was 4.8. Note that we're using the actual number of observations. We're using 5. We're not using sample observations, which would be 5 minus 1, or the total number of observations minus 1. Moving on from MAD, let's speak about variance, standard deviation, and Chebyshev's inequality. Variance over here, and I do suggest you set this up yourself. Set up your own Excel spreadsheet with these concepts and you will never forget them. Better still, create a video like this one and you will never forget it. At least you will know how to refer back to these concepts. So, variance, how that's calculated is the observation. As you see, I'm taking 30 minus 22, 12 minus 22. These are to the power of 2. Sum them up. And here we're dividing by the number of observations. Now I want to emphasize, and I'll draw this out too, what the formula typically looks like. So that was variance we just did. What the formula typically looks like is this in the math books, and this is a population variance. Okay. This is the observation minus, this is the population mean. That's not written out the cleanest, over the number of observations. Now I just want to emphasize that this is a population mean, and this is to the power of 2 here. This is a population mean. It is not the average of the sample. It is a population mean. And I keep writing these. They look kind of weird. What this does, when we're using this kind of a mean, is it actually gives us a bias. And it gives us a lower, because this is higher in the denominator. This is a higher denominator. It gives us an underestimated variance of the data set. So it is highly recommended to use by the way, these are typically your sample mean and your population mean are typically the same because you're not adjusting. So for instance, you're not changing your denominator to n minus 1 when you calculate your averages. You only do that when you're calculating your variance and subsequently the square root of this. This is the sum, is your standard deviation. So this over here, let's do the green. This over here is your variance, And the square root of the variance is your standard div. Okay? So this you'll see as variance, this you'll see as standard deviation. Only difference is to the power of. We're going to clear the canvas. Again, I highly recommend you write these out yourself. This was our variance, and as you see over here, our standard deviation is just the variance, the radical of the variance, or to the power of 1/2. That's variance and standard deviation. Actually, here, I want to show you sample standard deviation. Do you see how I'm doing n minus 1? Unlike previously, we're just doing n, which is the 5. This is variance to the power of 1/2 standard deviation. This is an example of sample standard deviation. And as you see, this is where the bias comes in. We call that a biased estimator. When you're not using sample, you see it's lower, it will give you a lower ranking of variance and of standard deviation, of risk, basically. So if you're using variance, let's get these guys. That didn't work out the way I was expecting it to. See, I want to back into this number. Maybe because, let's do -1 here. Yeah, that's fine. So I guess you can see that variance in Excel already uses the sample variance, because you see here I was using population. I couldn't back into it. The way I could is by doing n minus 1. It's already using the sample. Obviously, these values then give me a problem when I do the calc myself over here. Let's delete. Let me get rid of the 5. I'm going to show you then a standard deviation. You'll find a lot of here's standard deviation. I'll do the population standard deviation. Grab these guys again. Excel will have a lot of these calculations, and you can see I put back out. Let's do a standard deviation of the sample as well. Grab these guys. I always like to back into the data, and you can see we flip back to the sample as well. And that's the point as well of these refresher videos, is not only to help the end user with the terminology, but to also see it link and connect to Excel and how we can automate a lot of this information. Next up, Chebyshev's inequality. And this one is very much tied to the number of observations here that you will see fall under a certain amount of standard deviations. So there is a calculation that we can use. This is highly related to your typical normal distribution. And you'll see that normal distribution. And I do need to present this in a different way. So I'm not going to get too much into it, except to show you if you're looking at a data set and this is your average, this would be one standard deviation. And so this here would be 2. Let me use a different color. this is 2 standard. So this is 1 plus 1 minus 1 minus 2 minus 2, sort of standard deviations. So when you're looking at all the information contained in this data set, we're looking for different ways to explain what percentage of the information is here instead of in the outside tails. So you're trying to figure out how much is in the inside. And there's all these different ways. One that we do use is Chebyshev's inequality. This works for standard deviations which are over 1. So the standard deviation needs to be greater than 1. And once you have the calculation down, which is, let me get rid of this, which is 1 minus 1 divided by k squared. And that's basically it. This works for any distribution. K is a standard deviation. This k stands for a standard deviation. So it has to be over 1, so you could do 1.25, you could do 2. 2 with a normal distribution usually falls at 95%. So 95% of your data will be within 2 standard deviations of the distribution. When we do Chebyshev's calculation, or let's do this calc here. 1 minus 1 divided by 4, because it's 2 to the power of 2. Let's do this again. 1 minus 1 divided by 4. I'm getting a date, so let's do format cells general. I'll get 75%, and you can see 75% of the observations will lie within 2 standard deviations. This is basically how the calculations go. And 1.96 or 2 standard deviations will give us approximately 95% of observations if we're looking at a normal distribution. Now let me explain the difference between a normal distribution, which is symmetrical, and an asymmetrical or a not normal distribution. Let's go back to our terms. I'll get back to coefficient of variation and Sharpe ratio shortly. I want to get into a little bit into skewness, kurtosis, and wrap it up here. And then have a part 3. Again, these are refresher videos. This is going to lead up to a part 3, maybe a summary video. And the idea again being you're introducing concepts to an end user that will be using these terminologies for something bigger. So for instance, I want to introduce you to a portfolio after this. And this is the backup language I'm going to use to explain why I'm invested the way I'm invested and why I'm making recommendations the way I'm making recommendations. Skewness. If we're looking at our normal distribution, this is normal. This is positively skewed. This is negatively skewed. So negatively skewed has a tail that is more towards the negative here. And positively skewed has a tail, they call it the tail end, that is more towards the positive. Let's say this is 0, but here we can actually use even negative numbers. You could put the 0 here, -1, -2. But let's add the 0 here. You can see more of the values are lower, and it's got a tail that's positively skewed. There's more data, there's more observations that can be with higher values. Same here, more observations, but on the flip side, that can be lower values. So when we're describing data distribution, positive and negative skew speak to the way that the bell looks, and these are asymmetrical. How can I give you a memory system for positively and negatively? Just, I suppose for negative, just remember it, we're speaking about the tail of the data. So this is more towards the negative, this is more towards the positive. This is skewed right, skewed left. These are my memory systems. I'm sorry guys, I don't have a better memory system. Something else I want to show you connected with these. Let's say I am looking at a positively skewed data set. You will see here, this is the mode, M-O-D-E, mode. The mean will be more pulled right, okay? Because the tail here has more values, more higher values. You have more observations with higher values. So it's pulled to the right. And the median, you'll always find in between. So let's go again with negatively skewed. What you'll end up seeing is the mode here. And then you'll end up seeing the mean here. And then median. So if you're looking at trying to describe the order of things, how does mean, mode, and median come in? And I know you'll get these kind of things in some exams. Most of you that are familiar with the CFA charter will know there's certain things we're not supposed to talk about. So I'm not saying this is going to be on the exam, but these are ways you can remember how central tendency, a measure of central tendency, falls. So if it's positively skewed, you're going to have a mean that is higher, okay? Because these are higher numbers, yeah? This is 0, these are higher numbers. Let's say this is 1,000. So we're looking at the numbers this way, as opposed to we're looking at the numbers this way. Okay, so however you can remember this. Let's clear the canvas. And I wanted to then touch on kurtosis, coefficient of variation, and the Sharpe ratio. Coefficient of variation. Actually, let's do coefficient of variation really quickly. Coefficient of variation equals the standard deviation. So note that this is not with, where's the eraser? With to the power 2. So this is that sample standard deviation. This is sample variance. So we're gonna get rid of this sample standard deviation over your average of X. Let's say sample average. What this allows us to do is compare say a risk-free T-bill and the stock. It also allows us to compare a stock that is trading for $10 and a stock that is trading for $300. Because what we're looking at is risk and return. And these are percentages with bounds. So it helps us compare apples to apples. We call this, or in other words, we're comparing dispersion, this dispersion, again, how out is this, these returns? How much around the mean are these returns? That's what we're measuring with standard deviation, the risk. So we're comparing dispersion across different sets of data. And the reciprocal is the Sharpe ratio. So I just say the reciprocal is Sharpe. But there is a caveat here. This is supposed to be excess return, so a lot of people use minus the risk-free rate or the T-bill return. Okay? The easiest way I remember it is the reciprocal of the CV is the Sharpe. And then you can add stripping out your T-bill, your risk-free rate. Let's clear these. And lastly, to wrap up, I want to touch on, again, normal distribution. This type of distribution. And this type of distribution. Okay? So the red is normal. This is leptokurtotic or something. Let's go look it up. Leptokurtic. It's leptokurtic. This is leptokurtic. And this is like a platypus. Platykurtic. As you see, I also have a problem memorizing these. Platykurtic. Platykurtic. Maybe somebody can think of a good memory system for these. Like, I was thinking a platypus for the green one. But what we're basically saying is it is not as peaked as the normal distribution, or they call it the mesokurtic. So we're just speaking about the way the data looks. We're describing it. Is the data peaked? Is it more peaked? Is it less peaked? Are the tails fatter or the tails thinner? And what matters for risk management is this, what's falling in here, what's falling in here. As you see here, I got some major issues, right, with the leptokurtic, because I can have more data. More of my returns could potentially be in a danger zone. That's why for risk managers, the way that these look matter a heck of a lot. Let's clear the canvas. I want to show you how these are calculated really quickly, and that will wrap it up for us until part 3. So here, sample skewness, we do with x to the power of 3. This is very close to calculating variance, except we're doing it to the power of 3. And if you remember B5 and B6 in our calculations, we're basically here. We're taking observation minus mean, observation minus mean. So instead of like the variance doing it to the power of 2, we're doing it to the power of 3. This is skewness, and again, just to make sure, here I'll do, where is draw? Just to remind you of skewness, this is skewness. To remind you of kurtosis, I'm going to do normal, and then I'm going to do another one so you can see the difference. We're just trying to describe where basically we're always concerned with, let me see if I can find a different color. Always concerned with these tails, always what's falling in these tails, where's the data falling. So to the power of 3, sum it up, and then you divide by the number of observations, F10. Oh, sorry guys, I'm sorry, my mistake. You divide by the standard deviation, and I'm going to, you divide by the standard deviation to the power of 3. And I need to draw this out so that it doesn't get lost with the values the way that they're recorded. Again, this is for skewness. This is the calculation. It has to be multiplied by 1 over n. N equals 1. Again, we're doing observation minus sample mean to the power of 3. And the focus here, S, this is standard deviation to the power of 3. Okay? Standard deviation to the power of 3. That's for skewness. If we are dealing with leptokurtic or kurtosis, it will be this, but to the power of 4. Okay? And let me try and explain that we're looking at an axis kurtosis, axis kurtosis. It's again very similar to what we did earlier, but to the power of 4. We're summing it up, and again I want to show you this formula. You see this is the 1 over d11 is 1 over n, the number of observations. I'm thinking maybe what needs to be done is it ought to be n minus 1, since we are potentially using sample number of observations. I don't play around with the mathematics, basically, is what I'm saying. So here we're doing to the power of 4, and I'm taking that result minus 3. And just to tell you, when you have a minus, since the normal distribution is always a 3, if you have a platykurtic, which is what I have with my data, a platykurtic data set, you will get x less than the 3, so you'll get a negative result. If you have a left fat tail, you will get a negative on the skewness test. So this is what we have so far for part 2 on our refresher video on stats, probability, and quantitative analytics. And I hope you also found some of the applications to Excel telling, and they will assist you with some of your formulas and some of your administrative automation. I have one more video coming up. Thanks so much. You can find me under jasmine.com, and I'll catch you on the next one.